Good evening, everyone. Today we have an interesting topic which is called A Brief History of Metrization Theory. So we will start with Alexandroff. In 1923, he stated that a space that is T0 is metrizable if and only if it has a regular development. So what is a T0 space? Well, T0 spaces are spaces in which any pair of distinct points have a neighborhood in which one of them is contained but the other one is not. So the thing is that we don't know which point is contained. So you can separate the points, but not exactly. You don't really know how that separation is being done. So that's a T0 space. So that kind of a space is metrizable if and only if it has a regular development. So regular development means that, it's a property of developments. So we need to start first stating what a development is. So a development is of a space is a sequence of open covers such that for every point of the space, the collection of stars of the point is a local base at X. So you need to recall also that the star of a point is defined as the union of all the sets in that collection such that the point X is in that set. So if X has a development, it's called a developable space. Alright, so now what is a regular development? A regular development is a development in which for every natural number, because that's a development is a sequence, so for every natural number, for every pair of elements in an n+1 element of the sequence, if the intersection of those two elements is non-empty, then that means that the union of those two elements is contained in one element of the previous element of the sequence. So that's a kind of complicated definition, but that's what it is. And that's how the theory started. So from that point, which is 1923, we go 2 years later, in 1925, with the powerful theorem of Horizon. So Paul Horizon stated that every second countable normal space is metrizable. So this is important to mention because the Horizon theorem is usually explained with regular spaces and not with normal spaces. But in fact, the original theorem was stated in terms of normal spaces. So that's the theorem. And then 1 year later, Tikhonov in 1926 stated that the normality wasn't necessary because, as you may already know from topology, every second countable regular space is a normal space. So you didn't quite need the condition of normality. So it was enough to be regular. So in this year, we are already in the final form of Horizon metrization theorem. So yeah, for the proof of this theorem, you can Google that. There are tons of pages in which that theorem is explained. But the best explanation of that theorem is, in my opinion, given in the book of Topology by Moncrief. So you can check that. And then we moved several years later and to 1945 with the work of Schneider. Schneider stated that every compact space with a G delta diagonal is metrizable. So this is important because you know that if you are already familiar with the metrization theorems, you know that everything at the end of the day is stated in terms of paracompact spaces. So in 1926, we were talking in terms of regular spaces, second countable spaces. But then mathematicians gave a leap and started to talk about compact spaces and then paracompact spaces. So in 45, we already have a theorem about compacity. So that's the statement of the theorem. And here you need to recall that a topological space is said to have a G delta diagonal if its diagonal, which is defined like that, is a G delta set, which means that it is the countable intersection of open sets. Alright, so just 3 years later, we have the work of Stone that states that every metrizable space is paracompact. So now we are in terms of paracompact spaces. So you need to recall that a space is paracompact if and only if every open cover has a locally finite open refinement. So, and that in turn means, well, you need to recall what a refinement is. A refinement of a cover is another cover such that for every element of the refinement, there exists an element of the previous cover that includes that element. So this is important because, and this is a concept which is often misunderstood because in calculus we are already used to understand refinements as putting more points, dividing the line in more parts, right? So that's a refinement of a partition, for instance. But here, a refinement of a cover may not have more elements, in fact. Why? Because it is stated that every element of the refinement, for every element of the refinement, there should be an element of the cover that includes that element. To give you an example, if you have, for instance, a cover with, say, 100 open sets and an additional open set which is the whole space, then a refinement of that cover could be just about any collection that covers the whole space, because given that you already have the whole space as an element of the first cover, then any element of any refinement will be included in the whole space. So just to give you an idea that how this definition of refinement is different from the refinements of partitions that we study in calculus. So you have that definition, and then you know that a cover is said to be locally finite if for every element of the space there exists a neighborhood such that the set, which is the set of points that intersect that neighborhood, is not empty. That set is finite. So you have that. And then in 1950, you have the really important work of Nagata. And this is already close to the end of the early development of metrization theory. That states that, well, in fact, I gave myself some time to read at least some part of the paper, of the original paper of Nagata, and it states the following definitions. So the first definition is that an topological space for any R topological space and any index set A, we can denote as U alpha that sets of open covering. I mean, you have index set by alpha and open cover. All right, so you have that, and then you have an family of an indexes family of open covers, which is called an open basis, such that we you have that when you can represent any open set of the space as that formula. And that formula, I asked some mathematicians in the community, and that formula means just the union of all of those elements. So that's an old notation for union, very peculiar, but that means the union of the elements. I wanted to leave it at the original notation just to give you an idea how mathematics was written back in 1950. So you have that. And then Nagata states countability axioms called the beta countability axioms, which states that a space is beta countable if there exists an open basis of R consisting of a countable number of neighborhoods which are finite open coverings. Alright, so that theorem of Nagata is the following, and you perhaps already know that. It says that in order that a regular space is metrizable, it is necessary and sufficient that R satisfies the beta countability axiom. So why this theorem is so groundbreaking? Well, because opposed to the previous theorems, this theorem already gives you the characterization, the complete characterization of metrizable spaces. Because previously we only have conditions that imply that a space was metrizable. So now in this year we already know that. Well, granted, there are more ways to express those properties. I mean, in 1951, Bing established that a topological space is metrizable if and only if it's collection-wise normal and developable. So that's another set of properties that characterize metrizable spaces. We need to know what a collection-wise normal space is, and for that we first need to define what a discrete collection of subset is, and that is a collection in which for every element of the space there exists a neighborhood such that that neighborhood intersects at most one element A of that collection. So that's a discrete collection. And then a collection-wise normal space is one in which for every discrete collection of closed sets there exists a pairwise disjoint collection of open sets like that. So you have that family such that for every element A which were a closed set, there exists, the indexed open set that you defined previously. It includes that closed set. So that means collection-wise normal. And you can actually, if you know what a normal space is, you can actually understand a little why this is called collection-wise normal, because you have a closed set A, which is now included in another open set. So that gives you already the idea behind normality. Alright, so we are in 1951, and then this same year, a Russian called Smirnov published another characterization called, which is a paper, which is called a necessary and sufficient condition for metrizability of topological spaces. And I need to mention that that paper was written in, of course, Russian, and to my knowledge, there is no English version of this paper, but you can actually find the Russian version online. So I read that paper, and the important theorem is the following. Of course, that's written in Russian, and more or less a fairly well traduction is the following. So in order for a topological space R to be metrizable, it is necessary and sufficient that it be regular and it has a base which is called gamma, which is a countable union of locally finite collections. So this is already in the Nagata-Smirnov metrization theorem in its most current form. So, and I don't know how he proved that, because I didn't give me the time to actually read all of that Russian paper. But it's very likely that Smirnov already had or have heard the paper of Nagata. Because Nagata, in fact, didn't publish just one paper about that theorem, I found another one in which he's in the same year in 1950, in which he's making some comments about his theorem. So perhaps it's to be expected that Smirnov already knew that paper. But this is an important theory nonetheless, and it is the current form of the metrization theorem. And well, we already went through 3 different characterizations of metrizability. So the problem of which spaces are metrizable is completely solved. The question was answered positively. So one may think that this field of topology is already done for, in the sense that its main problem has already been solved, so there's not that much to do. But that's not actually true, because in the following years, in the following 10 years, to say that, there were many other characterizations of metrizability. For instance, this characterization by the same Nagata in 1957. So and the papers kept going, and I read at least 8 different characterizations of metrizability that are from the 50s and 60s, and we're already in 2025, so there is to be expected that there are a lot of more characterizations. So a first question will be, why are mathematicians so obsessed with a problem that is already solved? And the answer of that is because in the process of solving the problem, you actually find interesting things, like, for instance, Nagata in his paper was working with something called sigma spaces, and some of the conditions of metrizability that Nagata devised are something, or define something that now is called Nagata spaces, for say an example. So in the same process of solving the problem, you find new topics of research, because now you have defined Nagata spaces, and then you ask yourself, then what happens if you weaken some property of Nagata spaces? Then what happens? Which space now are now considered as a Nagata space, or as that kind of space? And how is that related with metrizability? Which property of metrizability you are losing? And so on. For instance, I also found another paper in which someone was defining something called M1 spaces, M1, M2, and M3 spaces. And then, M1 was included in M2 and M2 in M3. And every metrizable space was an M1 space. And also every CW complex was an M1 space. So that kind of a general space included both. But then the author was wondering how are the relations between those M spaces, like, is M1 equal to M2, is M2 equal to M3, and so on. So in the same process of solving some problems, you with the techniques that you develop, with that theory that you develop, you actually formulate new problems. So it's like a never-ending process of research. I mean, you solve problems, and in that process you formulate new problems. So it's kind of an endless endeavor, and mathematics is an endless endeavor in that sense. And that's pretty much how mathematics has been in the last few thousands of years. And that's also the reason why why mathematics has developed so many theories and has so many results, because we are never too comfortable with a solution. I mean, we solve a problem, and by solving that you find 3 new problems. So it is endless, and we probably have mathematics for the few next 1,000 years, even though AI may now be part of the equation. AI may now solve some theorems and so on. There is mathematics to be done for the next 1,000 years, and that's it. If you're interested about some part of this history of metrization theory, you can ask that in the questions. And if you want me to cover another topic, you can also put it down in the comments, and I will work on that. So see you later.